Good morning, everyone. Welcome back. We're in section 16.2 right now, so I'll just scroll back up to the top of the notes. We're looking at what are called line integrals. So we've been mostly focusing on, in chapter 15, integrating over regions in the plane or integrating over regions in space. Now we're integrating over curves. So these are known as line integrals or curve integrals, or sometimes commonly known as path integrals, just so that we don't always think that the curve we're integrating over is a line. So the line here is just meaning it's a one-dimensional object we are integrating over. And so we did a motivating example where we had a vector field. You can think of it as a force field, and we've got a path that a particle is traveling along through that force field. And we'd like to figure out what the work is done by that force field on that particle as it moves. So work is given by force times distance, but in this case, the force is changing as we move along the path. Not only is the force changing, it's also given by a different direction than the distance we're traveling or the direction we're traveling in. So we have to take that thing into account. So what we ended up doing was we said, well, we'll break up the path of the particle into little bits. And so we did that here. We said, okay, for a little bit of motion, what is the work done by that small change in position for the particle? And so that was done by the force applied on the particle, which was the F cos theta part, times the distance we've moved, which is that little ds. And if we do that for one little segment of the path, and then we add up over all of the segments and let the segment lengths go to 0, that turns into an integral. And that gives us this integral for the total work, which we found down below. And it's this integral, we'll look at this one here, which is sort of in its general form, the integral of the vector field dot the tangent vector for the path, integration with respect to t. That's the kind of integral we're looking at in this section. These are known as line integrals or path integrals of a vector field. And they are one-dimensional integrals. There's only one variable of integration. So that's the key here, is we're integrating over a curve. We're integrating over a curve. So along the curve, we're computing an integral. Then we saw there was two types. So I introduced two types. We can integrate a scalar field with respect to arc length, or a vector field with respect to a space curve. The part B, the vector field with respect to a space curve, was the motivating example above. And so then we started to look at these two types individually. So the line integral of a scalar field with respect to arc length, that's denoted by this integral here. So the integral of our scalar function, f of xy, over our curve c, and the integrals with respect to arc length ds. In order to evaluate that, we parameterize our curve with respect to some variable, in this case t, and the ds becomes the basically the speed times dt. So it's the magnitude of the length of r prime dt. This integral, this line integral of a scalar field with respect to arc length, we can think of as sort of the area of this curtain. So it's the area of the region trapped between the curve in the plane that you're integrating over and the corresponding curve up on the surface. The region trapped between those two forms like a curtain between them, and this integral represents the area of that curtain. It'll be the signed area if this curve is if this curtain dips into the region below the xy plane. So if it has negative f values, then it's really the signed area of this curtain. But that's one way to interpret it. And then we looked at a particular example where we computed the integral of the scalar function x with respect to arc length, where the curve was given by these two pieces. One was parabolic, the other one was a straight line. And so we had to come up with parameterizations for the curve. So there's our parameterization for that parabolic portion. And then we went and computed the integral for that. So that would have been the scalar function evaluated at the points on this curve. And then we multiplied by the length of the r prime vector times dt. And then what we did is parameterize the next portion of the curve. And that was that straight line segment. And then we did the same sort of integration of x ds. And then we added the two together. So that was the integration of the scalar function with respect to arc length. We can do that as well for, so that one was over a curve in 2D. We can do it over 3D as well. So suppose we've got a curve in space. So there's x is x of t, y is a function of t, and z is a function of t. Then the line integral of a scalar function f along the curve is precisely the same as it was before. We just have one extra dimension. So it's the scalar function times the ds component. And the ds component is the magnitude of r prime of t dt. In general, we can write this kind of integral in this way. So I can suppress, by just writing it like this, I can suppress whether it's 2 dimensions or 3 dimensions, because that's captured in the parameterized curve R. So both of these examples, the 2D and 3D example, boil down to this, that we are integrating over a parameterized curve from the value of its parameter, t, going from a to b, of the scalar function evaluated at the points on the curve, times the magnitude of the tangent vector, dt. And so this is our line integral of a scalar function with respect to arc length. So let's go ahead and look at one more example of this, and then we'll move on to the integrals of vector fields. So let's find the mass of a helix. So a helix, we're thinking of the helix as sort of a rod now that's been twisted up into this helix shape. And we know that the density at any point along this helix is given by that function rho there, x squared plus y squared plus z squared. In other words, it's basically its density is the square of the distance the point is from the origin. And the curve r of t that we're integrating over is given there. So what we'd like to do then is we'd like to find the mass of the helix. The mass of the helix is going to be given by integrating the density function, x, y, z, with respect to its arc length. So that's ds. And this goes from, in this case, it's, well, I'll put c here, but then it'll be from c, t equals 0 to 2 pi. So we're integrating over the curve this density function. And now at this point, you know, this is essentially our second course in integration. You've done calculus 2. We're now in calculus 3 doing integration. When you're using these kinds of ideas moving forward, what you want to just think of at this point is, you know, you forget all your formulas, and what is the raw essence of what it is we're doing? Well, what we're doing is we're saying we've got this rod that's been curled up into the form of a helix. What I'd like to figure out is what the density of the rod is. So if I chop the rod up into a bunch of little segments, each one of them is roughly the constant density, then all I do is take the density of that little segment and multiply by the length of that segment. So you take the density, multiply by the length, and you do that for a little tiny segment of the helix, and then you add up over all of those little segments. And that's essentially what this formula is saying. It's saying you take the density, you multiply by a little tiny length, ds, and then you integrate over all of those, sum them all up. And that gives you the mass of the rod in general. And so when we're seeing these integral formulas, I want you to always take a step back and go, okay, what is that integral formula telling me? Where is it coming from? So here it's just density times length, and then adding up over all the little bits, because the density is not constant. If it was constant density, there'd be no problem. We wouldn't need to really use an integral in some sense. We need to know the length of the rod, perhaps. And so that would be where the integral would come in. But if the density was constant, it would just be a multiplication of the density times the length. But since density is not constant, we chop the rod up into little bits, and we add up over the mass of all the little bits. And that's just the mass of the ith element right here, rho times ds. Okay, so
why do we do it over ds instead of dt?
So ds is the length of the rod. So what we have is I'm going to draw a straight rod, so just to avoid having to draw the helix. But if I want to find the mass of the rod, I look at a little segment of it, and the mass is equal to the density. Oh, sorry, I messed that second letter up. I'll change it. Density times length. So it's length that we're interested in. I see I'm hiding it behind myself. There we go. It's length that we're interested in. And length is ds, because that's arc length. That's the length of the rod. This rod's curving, so the length in this case is its arc length. Does that make sense?
Yeah, thanks.
So t is not the length. T is just a parameter which, depending on how we parameterize it, changing t could capture much more of the rod. If we're traveling along the rod faster, like twice the speed of parameterizing it in terms of arc length, etc. So arc length is the length, and that's why we're using it here, because that's what we want to use to compute the mass. All right, so now we can go ahead and start evaluating. So we've got that we are integrating over c. We're going to use its parameterization now. That's 0 to 2 pi. We are going to plug into rho the values on the helix, and then we're going to multiply by maybe I won't use a dot just to avoid confusion with the dot product. We're going to multiply by r prime of t dt. And that r prime of t dt, I'll just remind you, is what ds unpacks to, because ds dt is equal to r prime of t in magnitude. And so we're just using the fact that then multiplying through by dt, in other words, to get the differential, ds is r prime of t in magnitude times dt. So that's just unpacking it. Okay, so now that's the integral from 0 to 2 pi. Rho of t, rho of r of t. So that's going to be cos squared t plus sine squared t plus, and then the last one is z squared, and z is given by t, so that's t squared. So that's the rho of r of t, basically r of t plugged into rho, times the magnitude of r prime of t. So that's the magnitude of, we'll write down what r prime of t is. It's negative sine t, cos t, and 1. That's the derivative of r. We're taking the magnitude of that, and that's by dt. So we can do a little bit of simplification here. Cos squared plus sine squared is 1. So the density just becomes a 1 plus t squared. In other words, it really just depends on the height. And we've also got the magnitude of r prime of t, which is sine squared plus cos squared plus 1. So that's 1 plus 1 square root dt. And so that is root to the integral from 0 to 2 pi 1 plus t squared dt. Okay, so that's our integral simplified. I'm just looking to see.
The derivative of t squared not 2t?
We haven't taken the derivative of t squared. What we are taking the derivative of is, I'll put it in a different color. We're taking the derivative of the r function. So that derivative, and that derivative.
So we're not taking the PR of t. Oh,
There's no derivative there. Yeah, we're just plugging it in.
well, I was thinking like you would take the derivative of cosine squared t plus sine squared t plus t squared.
Nope, because that's that part. That's rho evaluated at the point on the curve. No derivatives there. Just evaluate the function rho at a point on the curve. And then the derivative comes in with just the parameterized curve. It's just, basically it's the tangent vector. We just want to find the tangent vector. So that has nothing to do with the rho part of it. Does that make sense?
Yeah.
Okay. So I'll indicate that here, that part was that part there. All right. And so now we can integrate. And it's the case with all of these ones in this section and the next section is our integrals are always just 1D integrals. They're always integrals with respect to a parameter. So these are just a single integral. I'll do one of them here. Sometimes I'll just skip the details because this is a calculus 3 or calculus 2 problem now, but we can just quickly work this one out. So the antiderivative of 1 plus t squared is t plus 1/3 t cubed, and that's going to be from 0 to 2 pi. And so this becomes root 2 pi plus 1/3 of 2 pi cubed. And then we plug 0 in, and that's just 0. So this is root 2 times 2 pi plus 8 pi cubed by 3. And so there is our mass of the rod with that density function.
Hi, Professor.
Hi there.
There's a small question. Why is it rho of RT?
Because we need to sample. So the rod is given by this expression here. So there's our sort of helix. And I'll draw some coordinate axes here. Maybe I'll change the color of the helix just so as to make it pop out. And then for that helix, what we're doing is I'm just going to grab a little section of it, and then I'll use my picture down here. So for my helix, I'm imagining, okay, I've got this rod. It's all bent, twisted up and whatever, but to find the mass of it, what I need to do is just chop it up into little bits, and I need to find a mass of a little bit. So in order to find the mass of a little bit, I need to know what is the density along that little bit. So I have to evaluate my density function at the points on the curve itself, because those are the points on the helix. So I have to evaluate my density function at a point on the curve. Those are the only points I care about because those are on the helix itself. So what is the density of a point on the curve? So if I imagine a little point here, I need to find the density of that little line segment. So I'm imagining it to be like a little straight line segment here. What is the density? The density is given by rho of r of t. And then I need to multiply by the length of it, which is the ds. And then that length we can unpack to be just r prime of t in magnitude times dt. Does that make sense?
Yeah. So is this formula like mentioned up top, like in the first slide you showed?
Formula for, I mean, this
for
is
the
this
rho,
is-
the rho one, the
this
rho
is the-
RT.
no, this is one we've used, well, I don't know, for forever, pretty much. Density, the density of an object, if we want to sample it at a point, it's just rho over the point. I mean, all we're doing is we're integrating over a curve.
The
So
point.
it doesn't make sense to evaluate the density at anything out, no other point, unless except the ones that are on the curve we're actually integrating over.
Yeah.
It's also, I mean, when we were looking at laminar plates, so we wanted to compute the mass of a plate. What we needed to do was we need to evaluate the density at a point on the plate. We didn't evaluate it at points that weren't on the plate, because they're not on the plate, so there's no mass contribution there. So that's what this is. It's telling us that we need to take the density function and evaluate it at a point on the curve itself in order to make sense of what the density at that point is, and then multiply by the length. Does that make sense?
Yeah, it does. Thank you so much.
You're welcome. All right, so line integrals of a vector field now. So we've just done scalar fields. And for the scalar fields, we've now, I'll back up just one bit here. So this was our interpretation of a line integral of a scalar field. We can kind of think of the scalar field as this sort of height function, if you will, along the curve. And so what we are doing is we are finding the area between the curve in the plane that we're integrating over and the values on the curve that sit above it, because we are evaluating f at the points on the curve. So that's how we can interpret it as an area problem. However, we just looked at an example of a density mass problem. There's no area in particular. I mean, it's not, we don't really interpret it as an area problem. All we do is interpret it as, if I want to find the mass, I take a length of a little line segment and multiply by the density of that line segment. And that gives me the mass of that little segment. That's exactly the same integral that came up here. It's just we weren't interpreting it as an area problem. So not all integrals have to be interpreted as area problems. We just saw the mass density one. You could reinterpret it as an area problem. You could say that, to get the mass, I'm going to take the area under the density curve, in other words. But that's not a necessity. We didn't have to think about it as an area problem. So this is the integral of a scalar field over a curve. We can intuitively think of it as an area of a curtain, but that's not necessary in particular examples. Now what we're doing is we are integrating a vector field along a space curve. So this comes back to our first motivating example at the very top of the notes, where we had a vector field and a particle traveling along a curve through that force field, and we wanted to find the work done by the force field. In that case, this was the integral we ended up writing down. It was the integral of the force field evaluated at a point on the curve, dot product with the tangent vector. So that basically gives us the projection of the force vector on a point on the curve in the direction of motion. And then we integrated over all of those. A shorthand notation for that is the one before it. So this one's shorthand. And that's the notation we'll use. And then we have to unpack it, just like the integral of f ds for the scalar vector field was shorthand for the integral of f times the magnitude of r prime of t dt. This is shorthand for that one that I put in a box. So the integral of the vector field evaluated at points on the curve, dotted with the tangent vector dt. And then the formula on the right is just an equivalent form. There we use the unit tangent vector. So I've absorbed some magnitudes into it and readjusted the dt in terms of arc length. The one in the box is the one we're going to use to evaluate these things. And it's common when we talk about vector fields to give each of the components a name, and basically each component is a scalar field. And it's common to use p, q, and r in the case of 3 dimensions, or p and q in the case of 2 dimensions. So I'm talking about a vector field. The x component is given by p, the y by q, and the z by r. And so that means that the integral that we're interested in evaluating, which is the integral of f dot dr, can be rewritten in terms of, if you expand out the dot product, it can be written as p dx plus q dy plus r dz. And the way this is really just happening here is we are noticing that when I take the derivative of r prime of t, what I get is x prime of t. Well, I'll write it like this. This might be a better way to write it. It's dx dt, dy dt, and dz dt. So when I take the dot product of the two of these, so when I dot product these, what I get is p times dx dt, q times dy dt, r times dz dt. And that's all that's written down here, except we've used the differentials dx, dy, dz instead of expressing it in terms of dt. And so we're suppressing the t in this case just for a shorthand notation. If we wanted to evaluate this, we'd put x, y, and z all in terms of t, and p and q and r all in terms of t, and evaluate. So these are just some shorthands to remember the integral. So let's go ahead and do an example. Get this all to make sense. So what we've got is a force field. It's given by capital F, which has got these components x, y, y, z, and x, z. And we're moving a particle along a twisted cubic curve given by that function r, that vector function r of t. And what I'd like to do is I'd like to figure out what the work is. So I need to figure out what the value of the integral is. And in order to do that, we'll just piece together the bits of information we need. We're going to need to know r prime of t, because we're going to have to dot that with the force field. So this is 1, 2t, and 3t squared. We're also going to need to know what f of r of t are. So this is our function f evaluated at points on the curve. So this is going to be x, y is our first component. And so I look at my function r, x times y is my first component. My second component is y times z. So that's y times z. And my third, oh, sorry, I'm using wrong ones. I'm using the ones from r prime of t when I should be looking up at r of t. So let's try it again. Maybe I think I did it right for the first component, but I've erased it, so now I can't remember. So x times y, that's t times t squared. So I'm using the fact that this is x, this is y, and this is z. So the next component is y times z, so that's t squared times t cubed. And the last component is x times z, so that's t times t cubed. So that becomes t cubed, t to the 5th, and t to the 4th. So those, or that's the value of the force field on the points that live on the curve. And those are the only ones we care about. For the whole force field, f of x, y, z, the fact that it's defined everywhere in space, we don't care about that. We only care about the values of the value of the force field on the curve that we are moving along. So that's why we do this substitution. Plug r of t into the force field and figure out what the force field is on the points we are interested in. And so now we've got our 2 bits of information that we need in order to set up our integral. So we are integrating over the curve of our vector field f dot dr. That's shorthand for the integral over c of f evaluated at r of t dot r prime of t dt. And so that's the integral from 0 to 1 of t cubed, t to the 5th, t to the 4th dot 1, 2t, 3t squared dt. So that is the derivative that is the dot product that we need to evaluate. I'm just checking to see if there's any new comments. Nope. Okay. So we now compute the dot product, and then that's our integrand that we're going to integrate. So the dot product is t cubed plus 2t to the 6 plus 3t to the 6 dt, or in other words, it's the integral from 0 to 1 of t cubed plus 5t to the 6 dt. And so really, as you can see here, it's really about the setup. The integrals in these cases are never that bad. They're just a single integral. We're used to, at this point in the course, we're used to doing double and triple integrals and having to pick order, etc. We're back down to just an integral of a single variable. And so the integrals never turn out to be really that bad. You could they could be made difficult. That's not to say you can't get a difficult integral like this, but for the most part in our examples, they're gonna turn out to be fairly straightforward. So in this case, we're going to integrate, and this becomes a quarter plus 5/7, and that's our resulting value, which is 20. Putting it over a common denominator of 28, we get 7 plus 20, which is 27/28. And so there's our final result. So that's the work done in moving the particle along this curve called a twisted cubic curve. As we move it through that force field.
So
Yep, go for it.
why is it not the magnitude of r prime of t?
Why is it not the magnitude of r prime of t?
Yeah.
Because this is a vector field now. This is a vector field. It's not a scalar field. So I have to convert it to a scalar function to integrate. And so I'm converting it by using the dot product. And this comes back up to our first motivating example that says, if I want to integrate a vector field along a curve, what I do is I can express it in terms of a magnitude. It's the vector, the part of the force field that points in the direction of motion. So that's that F cos, magnitude of F cos theta, times the distance that I'm moving through, which is the magnitude of r prime of t dt. But then we can unpack that and say, oh, that's really just a dot product. So I can get rid of the magnitudes in place of a dot product. And that's our integration formula, is involving a dot product now. So that's, I'll scroll back up to our integration formula. So our integration formula involves no magnitudes there. It's just a straight up dot product. And that's because we are integrating a vector field, not a scalar function. So in order to integrate a vector field, I had to use a dot product to get the projections down. Does that help?
Yeah, thank you.
Okay, you're welcome. So let's look at another example. We're going to evaluate this. So I'm going to call this, we're integrating. So this is a line integral. But when we first look at it, sort of the integral of c y squared dx plus x dy, it's very common to look at this and go, what is that? I'm not used to seeing dx's and dy's split apart in that way. Okay, I did mention that we would see it based on this formula here, but it still looks weird. So I am going to just unpack it. What does this notation mean? Because that's always helpful. So I completely agree. If you look at this and you're like dx, dy are split apart and it's an integral over, that looks very strange. Think of it this way. It's the integral of y squared x dot dx dy. And that we could write as the integral of c of y squared x dot dx dt dy dt, and then I'll put the dt on the outside, which you can't see because I'm hiding in front of it. There we go. So this is just notation. That all it is just shorthand notation, and I'm just unpacking the notation into a form that we can actually compute with. So I've unpacked that strange notation given in the question, and it really is just a dot product of our vector field dotted with r prime of, let's throw in a variable t, dt. So it's really just unpacked to that. And so from here, we can read off what is the value of our force field, what is our integral form that we're doing here. So this is the integral of a vector field over a curve. So that's the first thing to realize. Okay, we're integrating a vector field. So this falls under that form of integration of a vector field, not integration of a scalar field. So this is integration of a vector field over a curve. So let's jot that down. F of x, y. This is the vector field we are interested in integrating over, or we are interested in integrating over a corresponding curve. What is the curve? Well, we're given two parts. We want to integrate over a line segment, but we also want to integrate over an arch of a parabola. So in part A, I'll put a little subscript of 1, and part B, a subscript of 2 on those names for the curves, because those are the ones we're interested in. So part A, we are interested in integrating over this curve C1 that goes from -5, -3 to 0, 2. So I'm going to have to come up with a parameterization of that. I'll call it R1 of t. My parameterization is going to go from, okay, it's going to start at -5, -3, and I'm going to add to that a multiple of the vector that will get me to the other point. And so it's going to be the difference between 0, 2, and -5, -3. So this would be a 5 and a 2 minus 3, which is 5. So in other words, what I've written here is 0, 2 minus -5, -3. No, the tip minus the tail of that vector. So that's the vector that goes from the initial point to the terminal point. And so there's my curve that I'm going to integrate over, and it takes values from 0 to 1. 0 corresponds to the point I'm starting at, -5, -3, and when I put 1 in, I get the point that I want to end at, which is 0, 2. And so then I can go ahead and get some more of the information I need in order to do my calculation. I need to know what r prime is. That's just 5, 5. And so the integral over the C1 curve of f dot dr1 is the integral from 0 to 1 of our force field, our vector field, evaluated at points on the curve itself. So that'll be y squared. Y is -3 plus 5t squared. And then x is -5 plus 5t. And then I'm dotting that with 5, 5. In other words, r1 prime of t, and that's times dt. So that's the dot product I need to take. So that becomes basically it's a 5 times the first, a 5 times the second added up. -5 plus 5t dt. And at this point, it's a polynomial, so we're not learning much if I actually go through and expand and integrate. It's a fairly straightforward integral. It's just a little bit of algebra to rewrite it as a polynomial in its expanded form. So I'll just write down what the final result is. The final result is -5, 6. So maybe I'll put a dot, dot, dot to indicate that there is some work there to do, but that's nothing we haven't done already before. Part B is saying, now integrate over this part of a parabola, this arc of a parabola. So we need to come up with a parameterization for that piece. This will be R2 of t. What is R2 of t? So it's a part of the parabola. X equals 4 minus y squared. So if I take y to be my parameter, because x is already expressed in terms of it, then I get a 4 minus t squared. Y is t, and I just need to know what is the values of t that will sweep everything out. I need to go from -5, -3. So in other words, I need to go from a y value of -3 so that's my lower value of my t, to 0, 2. In other words, I need to end at a y value of 2. So there's the values of my parameter. And then we can go ahead and do the same work we did before. Take its derivative. That's going to be negative 2t and 1. We can go ahead and set up the integral. C2 in this case, f dot dr2. That's the integral from negative 3 to 2 of f, and f is, oh, it's still at the top there. Good, I can still see it. F is y squared x. So y squared is t squared, and x is 4 minus t squared. And we're dotting that with negative 2t and 1 dt. And we can go ahead and compute the dot product. Again, we get a polynomial, and it becomes a value of 40. I'm just looking it up for my pre-computed value, 40 plus 5, 6. And so that's the other one there. So the idea is, I'm sort of shortcutting this in the sense of I'm not doing stuff that we already know how to do. This dot product produces a polynomial. So you can work through the details yourself, but there's really nothing new there. It's do the dot product, you get a polynomial, and you integrate a polynomial, which you've done probably hundreds of times by now. Okay, the takeaway from this is that we had an integral that started at this point, ended at this point, and depending on which path we chose, whether we went along the integral, whether we integrated along C1 or integrated along C2, we got 2 different values. So these line integrals of vector fields, they depend on the path that you take. Just knowing the initial point and the end point is not enough to determine what the value of the integral is. You have to know the path you've taken through the vector field to get there. However, it turns out in special cases, you don't have to worry about the path you take. And those special cases are precisely when your vector field is what's called a conservative vector field. In other words, your vector field is the gradient of some potential function. We talked about a conservative vector field as an example in 16.1, but it turns out that these are precisely the vector fields where you don't have to worry about the path you take. And that leads us nicely into the next section, which is really all about that idea. So the next section is 16.3, known as the fundamental theorem for line integrals, is really about when can we not worry about which path we take. When can we just say, well, it starts at this point, it ends at this point. I don't care what the path is that went through the vector field. The integral is only going to depend on where I started and where I ended. And that's essentially what's called the fundamental, well, that's related. It's path independence, but it's going to be related to this idea in gradient vectors fields. So let's get into that. So this 16.3 is trying to answer the question, when can we get something like the fundamental theorem of calculus we had in Calc 2? Fundamental theorem of calculus said, if I integrated a derivative, I just needed to evaluate the antiderivative at the endpoints. I didn't care what the integrand's values were at any value between a and b. Those didn't matter. All that mattered was what is the value of the antiderivative at the endpoints. So it says the integral over the interval a to b of this integrand f prime, none of the values mattered in the interval. All that mattered was the values at the endpoints. So that's one way to think about what that says. And that's a nice way to think about it in terms of drawing up an analogy with what we're doing here. So what we're going to do now is we're going to say, well, what happens if I integrate a gradient vector field? If I integrate a gradient vector field over a curve, it turns out that that is independent of the values between the endpoints. All that mattered was the values at the ends. And why is that? Let's see. So let's recall that if I take the derivative of f of r of t, so this is a composition now. It's a scalar function, so little f, a scalar function or a scalar field, evaluated at points on a curve. If I take the derivative of that, I can use the chain rule. And when I do that, it becomes the derivative of f with respect to x times the derivative of x with respect to t, plus the derivative of f with respect to y times the derivative of y with respect to t, plus the derivative of f with respect to z times the derivative of z with respect to t. And if we look closely, we see, oh, that's just a dot product. That's the dot product of the gradient of f with, maybe I should say, evaluated at r of t, just so we know what it's being evaluated at. It's the dot product of that with r prime of t. Because r prime of t is just made up of the dx dt, dy dt, dz dt. And so what that means is the integral over this curve of the gradient of f dot dr is just the integral of the derivative of f of r of t dt. It's just that. Because that's what the gradient of f dot dr is. From the chain rules, just the derivative of f evaluated at the curve. And so now this is back into calculus 1. This is the integral of the derivative of something. And so by the fundamental theorem of calculus, we know that the integral is just going to be that evaluated at the values t equals a to t equals b. Or in other words, it's f of r of b minus f of r of a. And so that's the proof of this result. So if we're integrating a gradient vector field, that's essentially like it was in calculus 1, where we were integrating a derivative. And so we can compute it by taking the antiderivative. Here, if we're integrating a gradient vector field, we can compute it by just evaluating the potential function, which is some analogous sort of antiderivative to the vector field. And so let's go ahead and look at an example. We want to find the work done by this gravitational field. The first thing to note is that the gravitational field we've already figured out. It is the gradient of f, where f is equal to m, little m, big G over the square root of x squared plus y squared plus z squared. So in other words, integrating this gravitational vector field is really just the integral of a gradient function, because this gravitational field is a gradient vector field. So that means then the work is given by the integral of the vector field, which is the integral of the potential function, which by the fundamental theorem for line integrals, FTLI, which we can use as an abbreviation, is equal to f at the point 1, 2, 3 minus f of the starting point 1, 0, 0. And so there we go. We've kind of evaluated the integral by using, in some sense, I'm going to put antiderivative in quotes because it's not, in some sense, it's not an antiderivative, but it's noticing that the vector field was the gradient of a potential function. So we can evaluate the integral by just using the gradient function at the endpoints. And this ends up being little m, big G over, well, I'll factor that out and then we'll evaluate. It's 1 over the square root of 14 minus 1 over the square root of 1. And so there's our final answer in this case. So integrating gradient vector fields Very nice, very straightforward to do. I will finish in the next 30 seconds with just a summary of, I'm going to skip this because I can talk about it next day, but I want to summarize these properties. So I'll just sort of put them front and center. So this properties of conservative vector fields, this is related to this question of when does it not matter when I integrate from a single point to another point? When does it not matter which curve I take through the vector field? Turns out this is precisely related to conservative vector fields. And so these three statements are equivalent. If f is conservative, then it doesn't matter which path we take between the endpoints. The integrals will always be the same. So that is, the integral is independent of path. But it turns out that the converse is also true. If the integral is independent of path, then it means it's conservative. And lastly, if we integrate over a closed path, so a closed path just means you start at some point, you go around a path, and you come back to where you started from, that's a closed path. Starting and ending points are the same. If the integral around any closed path is 0, then f is conservative. And so this idea of being conservative meaning that f is equal to the gradient of some potential function. Being conservative means there's really independence of path in your integrals. So you don't have to worry about what path you're taking, just where you start and where you end. And if you start and end at the same spot, then your integral is going to be 0. So that's what we're going to finish up with next day, is just the proof of these three equivalences. And then do another couple of examples, and that's really it. So we've got all of the information essentially now, aside from a few proofs that I will do, to really go through and do all of these kinds of integral type questions. So I'll stop the recording now.